Estimating e to the 1.45 using a Taylor polynomial about x equals 2, what is the least degree of the polynomial that assures an error smaller than 0.001? In general, if you see a situation like this, where we're talking about approximating a function with a Taylor polynomial centered about some value, and we want to know, well, how many terms do we need? What degree do we need to bound the error? That's a pretty good clue that we're going to be using the Lagrange error bound, or Taylor's remainder theorem. And just as a reminder of that, this is a review of Taylor's remainder theorem, and it tells us that the absolute value of the remainder for the nth degree Taylor polynomial, it's going to be less than this business right over here. Now, n is the degree of our polynomial that we're in question, so that's the n. The x is the x value at which we are calculating that error. In this case, it's going to be this 1.45. And c is where our Taylor polynomial is centered. But what about our m? Well, our m is an upper bound on the absolute value of the n plus 1th derivative of our function. And that might seem like a mouthful, but when we actually work through the details of this example, it'll make it a little bit more concrete. So for this particular thing, we're trying to estimate e to the x. So I could write f of x. Let me write this way. So f of x is equal to e to the x. And we're trying to estimate f of 1.45. And let's just to get the bound here, to figure out what m is, let's just remind ourselves that, well, the first derivative of this is going to be e to the x. The second derivative is going to be e to the x. The nth derivative is going to be e to the x. The n plus 1th derivative is going to be e to the x. So the n plus 1th derivative of f is going to be e to the x, which is convenient. These types of problems are very, very hard if it's difficult to bound the n plus 1th derivative. Well, this, we know that e to the x, and I could even say the absolute value of this, but this is going to be positive, is going to be less than or equal to, let's say this is going to be less than or equal to e squared for 0 is less than x is less than or equal to 2. E to the x isn't bounded over the entire, over its entire domain. If x goes to infinity, e to the x will also go to infinity. But here I've set up an interval. I've set up an interval that contains the x we care about. Remember, the x we care about is 1.45, and it also contains where our function is centered. Our function is centered at 2. So we know we're bounded by e squared, so we can say we can use e squared as our m. We can use e squared as our m. We were able to establish this bound. And so doing that, we can now go straight to Lagrange error bound. We can say that the remainder of our nth degree Taylor polynomial, we want to solve for n. We want to figure out what n gives us the appropriate bound, evaluated at 1.45, when x is 1.45, is going to be less than or equal to the absolute value. Our m is e squared over n plus 1 factorial times 1.45, that's our x that we care about. That's where we're calculating the error. We're trying to bound the error, minus where we're centered, minus 2 to the n plus 1th power. Now 1.45 minus 2, that is negative 0.55. So let me just write that. So this is negative 0.55 to the n plus 1th power. And we want to figure out for what n is all of this business going to be less than 0.001. Well, let's do a little bit of algebraic manipulation here. This term is positive. This is going to be positive. This right over here, or this part of it's not an independent term, but the e to square is going to be positive. N plus 1 factorial is going to be positive. The negative 0.55 to some power, that's going to flip between being positive or negative. But since we're taking the absolute value, we could write it this way. We could write e squared, since we're taking the absolute value, times 0.55 to the n plus 1 over n plus 1 factorial has to be less than 0.001. Or since we want to solve for n, let's divide both sides by e squared. So we could write, let's find the n where 0.55 to the n plus 1 power over n plus 1 factorial is less than 0.001 over e squared. Now, to play with this, we're going to have to use a calculator. Remember, from this point, we're just going to try larger and larger n's until we get an n that makes this true. And when we want to find the smallest possible n that makes this true. But let's get out our calculator so that we can actually do this. So first, I'm just going to figure out what is 1,000th divided by e squared. So make sure it's cleared out. So let's take e squared. I'm going to take its reciprocal, and then I'm going to multiply that times 1,000th. So times 0.001 is equal to, so it's about, so I'll say, so it's 3 zeros. This is a 10,000th, and then 3 5. So it's 3 zeros. So I'll say 136. So this needs to be less than 0.123, and then I'll say 136. If I can find an n that is less than this, then I am in good shape. Actually, let me say this: less than 135. I want to be less than that value. Then I will be in good shape. This is a little bit more than 135, but if I can find an n where that is less than this, then I'm in good shape. So let me write this: 0.55 to the n plus 1 over n plus 1 factorial. So let's try out some n's, and I'm going to have to get my calculator out. So let's see, did I do that right? Yeah, 0.00135. If we get something below this, then we're in good shape, because this is even less than that. All right, so let's do it. Let's see what this is equal to when, I don't know, when n is equal to 2. I could start at n equals 1, n equals 2, n equals 3. But the more n, the further, if n equals 2 is good enough, then I might try n equals 1. But if n equals 2 isn't good enough, then I'm going to go to n equals 3 or n equals 4. So let's start with, actually, let's just start with n equals 3. So if n equals 3, it's going to be 0.55 to the 4th power divided by 4 factorial. So let's do that. So 0.55 to the 4th power is equal to that divided by 4 factorial. So divided by 4 factorial is 24. So that's nowhere near low enough. So let's try n equals 4. If n equals 4, then it's going to be this to the 5th power divided by 5 factorial. So 0.55 to the 5th power is equal to, and then divided by 5 factorial is 120. Divided by 120 is equal to that. We're almost there with n equals 4. I'm guessing that n equals 5 will do the trick. So for n equals 5, so let's clear this out. So for n equals 5, we're going to raise to the 6th power and divide by 6 factorial. And so let's just remind ourselves what 6 factorial is, 720. I could have actually done that in my head, but anyway. All right, so let's see. We're going to go 0.55 to the, remember our n is 5, so we're going to raise to the 6th power to the 6th power, and then we're going to divide by 720. Divided by 720 is equal to, and this number for sure is less than this number right over here. We got 4 zeros before this 3 after the decimal. Here we only have 3. So when n equals 5, it got us sufficiently low enough. This remainder is going to be sufficiently low. It's going to be less than this value right over here. So what is the least degree of the polynomial that assures an error smaller than 1,000? The answer is 5. Our n, if n is 5, we're definitely going to be under this.